Hi, welcome back to Workshop on Math as a Second Language, where today we begin what I think is a very, very exciting journey. I will call it the Chronicle of Human Endeavor. In other words, there's certain things that govern how society progresses. In other words, you didn't go instantly from people drawing pictures on the walls of caves to exponential notation or place value. It happens basically very, very gradually, okay? And mathematics, it sounds amazing, but you can actually trace the growth of civilization, the growth of human endeavor through how mathematics developed. It's almost like a love story, from writing pictures on the walls of a cave to exponential scientific notation. Here's how I describe the Chronicle of Human Endeavor. Okay? You're on a certain plateau and everything is going smoothly, but you come to an obstacle. And whenever you come to an obstacle, you have two choices. You can either agree that leave well enough alone and we'll stagnate down here, or you say, we have to find a way to get to the next step. So what happens is, to overcome this obstacle, it may take a while, but we eventually get to the next step. And then from the next step, there's what we could call a good news, bad news story. The good news is that from this vantage point, you can see better what's going on the step below than the people who are already there. That's the good news. The bad news is that you can see the next obstacle while the people down here don't even know that that obstacle exists. And so what happens is we keep going from obstacle to obstacle. And I suppose if you're very religiously inclined, you can say that we finally come to a plateau where there are no longer any problems, there are no more obstacles. And by the way, the scientist doesn't necessarily disagree. You know, they keep talking about this conflict between science and religion. There is no conflict. All the scientist says is, yes, that plateau may exist, but how will we know that we're there? In other words, how do you distinguish between an incurable disease and a curable disease for which there hasn't been found a cure yet? Well, the answer is you cure it, then you know it wasn't incurable. And even then, are you certain that 10 or 100 or 1,000 years down the road that cure might itself become a sickness and no longer work? See, in other words, all the scientist says is that we live in a probabilistic world. All we can really measure is, did we improve from one plateau to the next? And let's keep going smoothly until we come to the next plateau. And if there is none, so much the better. So actually, I called our journey from tally marks to place value. But surprisingly enough, the idea of using tally marks didn't occur for perhaps 1,000 years after people first were drawing pictures to represent things. Like, for example, it took people a long time to realize that 3 tally marks could represent 3 people, it could represent 3 horses. They felt that you had to draw the picture. And by the way, you can see examples of that in our vocabulary. See, what do you call 100 cattle? You say it's a herd. Well, what if it's 200 cattle? You don't say it's 2 herds, it's still a herd. I guess a herd is a lot of bull. Anyway, let's go on to the next. What do you call 100 sheep? Well, you call that a flock. Why didn't you call that a herd? Well, because sheep don't look like cattle. Look at how many different ways we have of talking about a whole bunch. You talk about a bevy of geese, a colony of elephants, an army of ants, all kinds of things this way. In other words, notice that how we described how many depended on what the noun was. So in other words, it doesn't sound like it was very, very advanced, but there was a big step involved in saying, hey, we can represent all of these things by tally marks. So now that was the first plateau. We've gotten rid of pictures, and now we have the tally marks. And what was the next plateau? Well, it's difficult to tell by looking how many tally marks we have. So what people decided to do was to arrange them in geometric patterns. And this is where the names like perfect squares came from. In other words, to make it easier to distinguish between 5 and 6. See, we just use these geometric patterns. We do the same thing with dice. In other words, look at how much easier it is. You look at this, and right away you see 5-ness. You look at this, and right away you see 6. You don't even count the dots. You know that this stands for this many, and this stands for this many. So much easier than just doing this alone. So in other words, geometric patterns was used not by the Romans, but by the Egyptians, who also used the place value system. They used the tally marks to stand for the numerals 1 through 9, but they arranged them in geometric patterns, okay? Now, again, what do you think happened? Remember what we said, you go along smoothly till you come to the next plateau. Well, the next plateau was what happens when you have lots of tally marks. See, 5 or 6 was easy to keep track of. Look at these 2 rows of tally marks. Is it obvious just by looking which line has more and how much more? No, you say, well, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You say, oh, it's easy. This row has 2 more than this. But remember, we're back at the dawn of consciousness now. We haven't learned place value. Here's primitive man trying to decide who has more cattle. One has this many, one has this many. Well, one thing they can do is they can count in what we call a one-to-one correspondence. They can say 1 for me, 1 for you, 1 for me, 1 for you. Keep counting this way. And when they get all through, they see what? When there's none left on this line, there are 2 left on this line, okay? To put this in more simple terms, suppose there are a certain number of people in the room. People are seated. Everybody is seated, 1 person to a chair, and some of the chairs are still empty. Well, without even counting, you know there are more chairs in the room than there are people. But this becomes very cumbersome, counting 1 for me, 1 for you, especially if the numbers get much bigger. So what the Romans did was kind of interesting. They said, okay, let's use some letters of our alphabet to stand for numbers. The I's looked like 1, so they used I to represent 1. Now in counting, they said, we have 10 digits, 10 fingers, so every time we come to 10, we'll cross them out. Now, just by looking at this, it's easy to see you have 12 because you've invented the abstract symbol, the crossing out symbol, to stand for 10. There's no way of looking at this symbol and recognizing that it stands for 10. You have to be told that. But once you know that, see, what you do know looking at the symbol is there's 1 crossing out symbol and 2 tally marks. Well, what the Romans said was, well, look, the crossing out symbol looks like the letter X. X is a letter of our alphabet. So let's use X to stand for 10. And then 10 tens. So you're going to trade in by tens. You can count on our fingers up to 10. When we get to 10 tens, that's 100. That's where the C came from. The Latin word for 100 is centum, C-E-N-T-U-M. And then when you have 10 C's, we'll trade that in for an M. M was the Latin word for 1,000, milla, M-I-L-L-A. In fact, the number that we call 1,000 would have more appropriately been called 1,000,000, but that's just a historical thing. So now with these symbols, look what you can do. See, if I look at this, I have what? 2 M's, 3 C's, an X, and 4 I's. 2, 3, 4, 5, 6, 10 symbols altogether. And what does it stand for? 2 M's is 2,000, the 3 C's are 300, 110, and 4 ones. In other words, this Roman numeral takes the place of 2,314 tally marks. Still more complicated than how we write it. But look at what an innovation this is. What an improvement over having to write 2,314 separate tally marks. And you see, when you can express numbers in a compact form, it allows you to think in terms of bigger bundles of numbers. In other words, in terms of tally marks, something like 2,314 would be overwhelming. But you see, we gradually came away with ways of visualizing numbers. This was the Roman numerals. And by the way, newer isn't always better. I don't know if you still teach Roman numerals in school, but when I went to school, we also learned that V stood for 5. Where did they get the V from? Well, 5 is half of 10. So they just took the half of the X that looked like the letter V, and that stood for 5. L stood for 50. D stood for 500. In other words, this is an interesting thing, how numbers and numerals became confusing. You know, I once had a student show me, this was a 4th grader, show me why 4 plus 5 was 10. And I said, how'd you get that? And he said, well, here's 4, and now I'll tack on 5 more. 1, 2, 3, 4, 5. And see, what's happening is the number, the word 10, can be written by using 9 tally marks. All kinds of little things you can do by confusing the number. For example, why is half of 8 equal to 3? See, half of the numeral 8 looks like the numeral 3, but half of the number 8 is not the number 3. Now, see, what happens with the Roman numerals also is they said, if you put a smaller denomination in front of a bigger one, it means to subtract. So xi would mean 11, but ix would mean 9. Now, you see, this goes against visualness. If you have a $10 bill and a $1 bill, it's $11 no matter whether you start with the 10 and add the 1 or whether you start with the 1 and add the 10. The reason that the Romans did this was that they only used Roman numerals to number pages. So it was much easier to write this than to write 9 separate tally marks. It was much easier to write this than to write 6 separate tally marks. But notice that in the original Roman numerals, it wouldn't make any difference how you arrange these. See, for example, what do you have here? You have 3 M's. Well, you also have 3 M's here. You have 2 C's. You also have 2 C's here. You have an X here. Also have an X here. You have 4 1s here, 4 I's. You have 4 here. These are the same number. And that agrees with reality. In other words, you can give students a bunch of play money and then give them a second batch of play money and see how they arrange the 2 batches. They'll probably group all the hundreds together, all the tens together, all the ones together. Well, you see, what happens is this is now a huge innovation, but as science improves, numbers are getting bigger and bigger. And pretty soon it's not enough to talk about thousands. The concept of 10,000s, 100,000s, millions, these all lie ahead. Are we going to invent a new Roman numeral or a new symbol for every time we come to a new group of 10? That would be very, very tedious and very, very difficult to do. And so that was another obstacle in the plateaus that people had to overcome. And so the next thing that was invented was something that was called the sand reckoner. That's in Western civilization. In Eastern civilization, it was called the abacus. What people did was they drew lines in the sand, parallel to each other, vertical lines. The first line to the right would be ones, the next line tens, the next hundreds, the next thousands. This is the first example of place value. You see, all these lines look alike, but we can tell which line is which by its position. In other words, this line looks like this line, but this line is the ones, this is the tens, the hundreds, the thousands, etc. And now to keep track of the denominations, for example, suppose you saw something like this. They took pebbles, put them on a line, and what would this say? You have, this is still 1 pebble, but it represents thousands. This is 3 pebbles, but it represents hundreds. 2 pebbles, stones actually. 4 represents 1. This would be the abacus, the sand reckoner's way of saying 1,324. And by the way, just as an interesting piece of folklore, the Latin word for stone is calculus. Okay? So that's where the word calculate came from, to do arithmetic using stones. So, in other words, all of math could have been unified by calling first year math calculus 1, calculus 2, calculus 3, calculus 4, but that's all calculus means, okay? Except one of my students once told me sort of a ribald story about calculus and stone don't mean the same thing, because you don't say a man went out, had a great time, and came home calculus. No, calculus and stone mean the same things as nouns, and there is no verb for calculus, okay? But I just thought I would tell you that story because this is how some of the students sometimes think about math. So that's the sand reckoner. If I wanted to represent 3,124, that's what? 3 thousands, 100, 2 tens, and 4 ones. So what would that mean? I would put 3 on the thousands line, 1 on the hundreds line, 2 on the tens line, and 4 on the ones line. See, and now every time I wanted a new denomination, I wouldn't have to make up a new symbol. I would just use another vertical line to the left of the ones I had already drawn. And again, this lecture has gone on, I think, long enough, gives you enough to think about. I thought we should go to our closing problem right now, our practice problem. In Roman numerals, XXI represents the odd number 31. See, 10 plus 10 plus 10 plus 1. If X had been chosen to represent a number other than 10, would XXXI still represent an odd number? Okay? You may think that's kind of a silly question, but it does lead to something that's quite interesting that I'll mention in our solution. But for now, pause the video, tackle the problem, see what answer you come up with, and then come back and watch what I did, okay? See, look what happens. If X represents an even number, even plus even is even plus odd is still even, okay? So this is an even number, 1 is an odd number, even plus odd is an odd number. See, in other words, if X stood for 4, see, 4 plus 4 plus 4 is 12, that's an even number, plus 1 is an odd number, it's 13, okay, so the answer is an odd number. But look what happens if X represents an odd number. If X is odd, remember, odd plus odd is even, and even plus odd is odd. So if X is an odd number, X plus X plus X is still odd. Check it out. If X is 5, 5 plus 5 is 10, plus 5 is 15, that's an odd number. 1 is an odd number, so odd plus odd is even. So in other words, if you were trading in by 5s, 3 5s and a 1 would be the number 16, right? 15 plus 1 is 16. 16 is always an even number, but look what happens. It ends in an odd digit. In other words, we teach kids to say a number is even if it ends in an even digit. It's odd if it ends in an odd digit. But that's only because the trade-in value was an even number. If we traded in by odd numbers, the result would be different. In other words, in our arithmetic system, how the tables look and what the properties are depend on what the value is that we're trading in by. That will be a topic much later in our discussion, but I just thought I would introduce that now. I think that's about enough for today, and I'm going to look forward to seeing you all next time. Have a great day.